Ever wondered how we might combat the growing threat of antibiotic-resistant bacteria? It's a problem that's been escalating over the years, causing a staggering 2.8 million antimicrobial resistant infections every year in the United States alone, and leading to 5 million deaths worldwide. But there's a glimmer of hope on the horizon, a potential solution that's as fascinating as it is tiny. It's called phage therapy. In essence, phage therapy harnesses the power of phages, which are minuscule viruses that possess the unique ability to target and annihilate bacteria. This remarkable treatment is currently being explored in clinical trials, and it's showing promise as a viable weapon against antibiotic-resistant infections. As bacteria are attacked by phages, they can lose their resistance to antibiotics, making them vulnerable once again. Phages might be tiny, but they pack a punch when it comes to battling bacteria. Phages, or bacteriophages, are tiny viruses that have a unique ability. They're not your typical viruses. Instead, they're kind of like tiny natural predators that prey on bacteria. Imagine you're in a forest and you see a tiger stalking its prey. This is what a phage does on a microscopic level. They latch onto specific bacteria, inject their genetic material, and use the bacteria's own machinery to reproduce. This process eventually causes the bacteria to burst, releasing more phages that go on to hunt other bacteria. In nature, this cycle helps control bacterial populations. Phages are essentially the predators of the microbial world, keeping things in balance. What's even more intriguing is that phages are highly specific. They only attack certain types of bacteria, leaving the beneficial ones unharmed. Now, why is this important to us? Well, with antibiotic resistance becoming a significant concern, we're in desperate need of new ways to fight harmful bacteria. And that's where phages come in. So, these microscopic predators could be our secret weapon in the fight against antibiotic resistance. But how exactly does phage therapy work in practice? Well, phages, these microscopic allies, are genetically programmed to target specific pathogens. Imagine a lock and key scenario. Each phage has a unique key that can unlock and infiltrate a specific type of bacteria. Once inside, they replicate, causing the bacteria to burst and die, while releasing more phages to continue the cycle. Moreover, phages are experts at adaptation. They evolve with the bacteria, ensuring their keys can keep up with any changes in the bacterial locks. This makes them an incredibly potent tool against antibiotic-resistant infections. Now here's the exciting part. When bacteria are under attack by phages, they can lose their resistance to antibiotics. It's like the phages distract the bacteria, leaving them vulnerable to an antibiotic offensive. This unique 1-2 punch approach of phage therapy is currently being explored in clinical trials with promising results. Phage therapy has the potential to revolutionize the way we treat bacterial infections. By harnessing these natural predators of bacteria, we may be on the cusp of a new era in medical science. The proof, as they say, is in the pudding. Let's explore some real-life examples of phage therapy. Cynthia Horton, a woman plagued by recurrent ear infections, turned to this innovative treatment when antibiotics failed her. Her ear bacteria happened to be a match for a rare superbug, a villain causing severe eye infections and other complications found in certain brands of eye drops. Enter our heroes, the phages, genetically programmed to target specific pathogens. They attacked and the bacteria lost their resistance to antibiotics. Then there's the case of Tom Patterson. His drug-resistant infection met its match in a phage cocktail, courtesy of his wife, Stephanie Strathdy, who surmounted obstacles to deliver this therapy to his doctors. The battle was won, and Patterson was cured. These are but two examples of phage therapy's potential. Phage scientists are tirelessly working to optimize this treatment, and clinical trials are underway for various infections. The success of these cases gives us hope for a future where antibiotic resistance is no longer a looming threat.